In section 4.7, we'll learn about inference for experiments, where we take the results of an experiment and we apply it to a broader population. Here we have what's called a design diagram for the experiment that we created over the last few sections. We started with 20 volunteers, and we randomly assigned them to two groups of 10 students each. One of those groups got treatment 1, which was the soda with caffeine. The other one got treatment 2, which was the soda without caffeine. And at the end, we measured our response variable, which was the pulse rates, and we compared the average change in pulse rates across both groups. This is a completely randomized design because the experimental units, or subjects in this case, are assigned treatments completely at random. Let's create a design diagram for another experiment where we investigate if magnets can be used to help patients with chronic pain. We'll start with 50 patients. A doctor is going to identify a painful site on each patient and ask them to rate the pain from 0 to 10. The doctor then selects a random envelope containing a magnet. Now, some of these magnets are active and others are inactive. The chosen magnet is applied to the site for 45 minutes. This is the randomization. We have two groups. Half of them are receiving an active magnet, half of them are inactive, and the doctor doesn't know which patient is receiving which type of magnet. After being treated, the patient again is asked to rate the level of pain from 0 to 10, and the improvement is recorded. At the end of the experiment, we'll compare the mean pain improvement. Anytime we conduct an experiment like this, we're hoping to see a statistically significant result. What does that actually mean? Well, it means that we want to see a difference between our two groups, the treatment and control group, that's large enough where we can attribute that difference to the treatment. So when we ran this experiment, the doctor chose an envelope at random. He didn't know if he was picking an active or an inactive magnet, and he had this patient apply that to the pain site. The purpose of this random assignment was to create groups of patients that were roughly equivalent at the start of the experiment. Now, that's not going to be exactly the case, regardless of how many times that we do it. Our two groups hopefully are close, but it's very unlikely that they're going to be exactly the same. So it's possible that to start, the active magnet group included more patients who are going to feel better regardless of whether or not they receive an active or an inactive magnet. So after these patients have held the magnets on their pain site for 45 minutes, we ask them to rate their pain relief. And let's take a step back for a minute and assume that these magnets do nothing. They don't help reduce pain at all. It's still really unlikely that we'll see exactly the same results in both groups. One of these groups is going to have more pain relief than the other, simply because there's variation in the amount of pain that a person experiences at any given time. In addition to that, some of them might be influenced by the placebo effect. So these results are going to be split pretty much down the middle, where about half the time the active magnet group is going to have more pain relief than the inactive group, even if the magnets don't do anything at all. So if we get to the end of our experiment and we see that the active magnet group did report better results, how do we know that that's because of the treatment and not just because of chance sampling variation due to the random assignment of our subjects? So that's what statistical significance is. We want to see a difference that's larger than we would expect just by chance variation in the amount of pain relief these subjects are reporting. Now, eventually we'll be able to quantify this mathematically, but right now it's just the concept that statistically significant means that we have an observed difference in responses between groups that is so large that it's unlikely to be explained by chance variation. The magnet experiment, as described, was a real experiment, and these are the results. Our top dot plot here shows the patients that received the active magnet. We can see that their pain relief varied from 0 to 10, and the bottom group here received the inactive magnet. Their pain relief varied from 0 to 5. The average of these two groups, the mean improvement for the active magnet group is 5.24, and for the inactive magnet is 1.10. So all of these pain reliefs are either placebo, or they just would have happened regardless of which magnet type they were given. The difference between these two is 4.14, and this is a statistically significant result. In other words, this result is large enough for us to attribute it just to chance variation, and instead we can say that's because of the magnets. In this next example, we want to see if talking on a cell phone is more distracting than talking to a passenger. A researcher randomly assigned 48 subjects to each of these treatments and observed the proportion that were distracted enough to stop at a rest stop. First step, we want to calculate the difference in the proportions of these two groups, passenger minus cell phone. So in the passenger group, there were 24 subjects, and 21 of them stopped at the rest stop. This is this fraction right here. Cell phone group, it was 12 out of 24. When we subtract those two proportions, it's a difference of 0.375 or 37.5%. So is that difference statistically significant? To figure that out, we're going to run a simulation based on the results of our experiment. So in our table here, we see that we had 48 total subjects. 33 of them stopped at the rest stop. 15 of them did not. So imagine we have 48 blank index cards. We're going to write stopped on 33 of them and didn't stop on the other 15. We shuffle up those index cards, and then we deal them into two piles of 24. We want to see how likely is it to result in something like this, where 21 of those 33 end up in one pile and not the other. So looking at this simulation dot plot here, okay, this is showing 100 trials. If we write all that information on those index cards, split them into two groups, and do it 100 different times, these are the differences that we get. Anything to the right of this gray line here are situations where the passenger group ended up with a higher proportion. Anything to the left over here is when the passenger group had a lower proportion. Right in the middle, we have 0, because this is simulating a situation where there is no difference in those proportions. All of the differences we see are just because of chance variation. So part B notes that there's a blue dot at a difference of 0.125 and asks us to explain what that dot represents. Now, every dot in this dot plot represents a single simulation where we dealt out all 48 cards into a passenger group and a cell phone group. Each of those had 24 cards in it. And then we recorded the difference in the proportions of people who stopped at those rest stops. This particular blue dot is just one of those possible random assignments in which the difference was 0.125, meaning the passenger group was higher by 12.5%. Part C, is the result from part A statistically significant? What do we think based on this graph? Well, the difference that we saw in part A was 0.375. That's out here. Okay, that's higher than literally every simulation that we did, all 100 of them. So the result that we got based on the experiment was higher than every single simulation that we ran. That's telling us that this is a statistically significant result. It's unlikely to happen just by chance alone due to chance variation in the random assignment. So how unusual does a difference have to be before it's considered statistically significant? For now, we can use a boundary of 5%. Anything that happens with less than 5% frequency, we consider unusual and unlikely to occur by chance alone.